Alright, let's finish off Chapter 4 notes before I do some sample problems from the textbook. So we left off last time on main concept 2 for circular motion, and it was basically just giving you the formula for centripetal acceleration. And we know that acceleration is a vector, so this gives you the magnitude, but a vector also needs direction. And so the centripetal acceleration points towards the center of the circle. Always. If you're here, points that way. If you're here, points that way. Now, the book derives this for you. I'm not going to derive it for you. In fact, I always forget it. I'll learn it 1 year, and then a year later, I'm like, oh, how did that go? I don't remember. If you're interested, you're not responsible for really knowing it. If you're interested in it, you can take a look at it in the book. It's on, let me see where it is. Yeah, it's on page 71 in your book, where it says proof of equation 4-34. Not only does it prove it for the magnitude a equals v squared over r, but it proves it for the direction. At the very bottom, you'll see tangent phi or phi or whatever, phi phi pho phum equals tangent theta with some stuff in between. That's proving that those angles are equal, so that the centripetal acceleration points towards the center. You can go through that. If you have any troubles with that, ask me and I'll help you go through that. And yeah, but really all you need to know is that it points towards the center, and that's important. So that's circular motion. And let's get through relative motion. Now, relative motion mathematically is easy, but conceptually is just often seem mind-boggling until you get some experience under your belt about how to handle these problems. The first thing to talk about, though, is that velocities are relative, but accelerations are not. That's because velocities, and even actually positions, I should put positions in here, they depend on your point of view. If you are at rest on the ground, then someone on the ground also sees you at rest. If you're at rest in a bus, then someone on the ground sees you moving with the bus and at the same speed as the bus, even though from your point of view, in both cases you're at rest. Acceleration, on the other hand, is not relative because, as we're going to learn next chapter, Newton's second law, in order to get an acceleration, you need to apply a force. And forces don't depend on your point of view. Forces are, in one sense, universal. A force on a train or a bus is a force off a bus. So accelerations are not. And this comes into play in the textbook problem that you'll have to do with the cheetah and the cameraman and the crewman. And every other one actually, to be honest, but that one is really important there because they ask you about the acceleration in one point of view and in the other point of view. So kind of gave you the answer, gave away the answer there. Yeah, that's all I need to say for that. Relative motion, concept 2. You can use similar triangles with 2D relative motion that I did it again. I forgot to change it here. That doesn't have acceleration. Let me just be picky here. Sorry about that. It doesn't have acceleration. So what does that mean? That means that if you don't have acceleration, then this equation this term goes away because acceleration is 0. So you got basically delta x equals v naught t, or if you want to just write it differently, distance equals speed times time. And you can see that if the distance doubles, the speed doubles. So if there's no acceleration, those change the same way. And I mentioned back here that velocities and positions are relative. So another way of saying that is distance is relative and speed is relative. So for example, if you have a triangle that represents relative motion in terms of speed, meaning if you're in a boat going this way, headed this way, if your motor is pointing this way across the river, but the river is flowing down this way, then the boat is actually going to have an overall velocity this way with respect to the shore. So you can say this is velocity of the boat. I'm not going to go into this whole with respect yet. I'll do that when I get here. You can say this is the velocity of the river, and this is the velocity with respect to the ground. If you're on the ground, this is what you would see the boat actually doing. Now, you can use similar triangles. This is like the distance across the river. Crossed. This is the distance downstream, and this is the distance the boat actually travels. Now, the distance the boat travels and the velocity with respect to the ground are not equal numbers, but you do know that these angles are equal, which means, let's say the distance is bigger in magnitude than the velocity. These are similar triangles. Same angle, same angle, same angle, same angle, but the sides are in proportion even though they're different lengths. So that's all that's saying. Finally, main concept 3, relative motion. What is this with respect to business? Let's put it this way, and if this confuses you, you can ask me to go further, explain it further in class. But let's say you had big floaty shoes on, so you could walk on water, right? And here's a river. And the river is flowing. This is like land. This is the shore. This is the shore. So the river is in here. Let's say the river is flowing this way. If you're in a boat starting here, and you have your motor pointing straight across, so that if the river wasn't flowing, you would go straight across. But anyway, you have your motor pointing that way, and then you start going. You're gonna head that way, but the river's gonna pull you down this way, and you're gonna go like that. It's gonna pull you downstream, so you end up somewhere farther down. So if we say your velocity with respect to the water, what that means is if you were standing on the water with your big floaty shoes, yeah, but you didn't have any like motion this way, you have no motor stuck to you, or you have no paddle, or you're not running across the water, you would still be pulled downstream. So that means your motion would actually, you would follow this path, because you're going downstream at the same rate as the boat, because the river is pulling you with at the same rate. So what does the motion of the boat look like from your point of view? Well, it looks like it's going straight across the river. Of course, you can see that you're moving downstream, but let's say there's a big wall here blocking your view of anything beyond the shore. And whoops, disregard this line here. And let's say there was a big wall on this shore blocking your view, so all you can see is river and wall, and the wall is so uniform that you can't tell if you're moving with perspective. There's no like little holes that you can use to judge if you're moving down the wall. then really you just see the boat moving straight across because you're moving with the boat. If the boat's here, you're here. If the boat's here, you're here. So you can see it's always directly in front of you. And if you think about it for a sec, that means that it looks like it's moving straight ahead. So with respect to the water means motion relative to something as seen from an observer not moving on that something. So you're not moving on the water, you're just standing on the water. You happen to be flowing downstream because the water is pulling you downstream, but for all practical purposes, you're not moving with respect to the water. The boat is. And so, I don't know if that makes sense. That's the best I can do for now. I'm sure, excuse me, it's going to make sense for some people and not make sense for other people. If you're the other people, don't feel bad. This is not an easy concept. Just ask me in class. I'll clarify. That's how this class is set up. Think of it like this is a lecture I might have taught in a typical classroom. I would have taught you the same thing in class. Some of you would have been confused and you would ask me a question and I would have answered it and hopefully cleared things up. We're just doing things a little differently. I'm giving the lecture on video so you can watch it whenever, and then you can still ask me in class just like normal. Just ask me whenever you see me and I get a chance to talk to you. Alright, that does it for Chapter 4, 2D Motion. I'm going to do a few sample problems from the textbook so you can look at those to help you get an idea how to do book problems, especially projectile motion problems. And yeah, I'll see you in class.